Good morning. So we are here to take you with us on Zomato's logging platform journey and how we ended up saving $1 million in the process. Let me just introduce myself. My name is Anmol Virmani. I'm a platform engineer at Zomato, and we build platforms for petabyte scale. Along with me is my colleague Palash.
Hi, I'm Palash. I work as a platform engineer at Zomato, same as Anmol. Yeah.
All right. I don't think I need to tell anybody what Zomato is. Okay. For those who don't know, it's a platform that connects customers with restaurant partners and delivery partners and serve their needs intermediately. So we had to have a steady and great supply of restaurant and delivery partners that would make the customers happy. Happy customers would lead to more demand. That would eventually lead to more restaurant partners in the process. And then we have more delivery partners. And this is a continuous process. So we don't have like one customer that is the person who orders food. We have three customers. We have restaurant partners, delivery partners, and the customers actually who order food. So we make products and run hundreds of experiments each time because we have to give a better experience to all of them. And in the process, we want everybody to have, we urge our developers so that they add metrics, logs, events at each part of the journey so that we have observability of the platform and we can see what's going on in the system. This mindset led to huge logging by the developers that tended to 60 terabytes of logs every day, coming at 150 million events per minute. And this is what we made a platform for to solve this. Before we move further, why do you think we need a centralized logging platform? Anybody? All right. So when we are running into a microservice architecture, hundreds of services, thousands of pods are running, we would want to get a holistic view of what's happening at one place. And we can switch between environments, switch between services, and see all logs at one place. So before we were presented with, OK, you have to solve this logging platform problem, this was the problem statement that we were given with. We had an ingestion rate of 150 million per minute, 60 terabytes of logs every day, 30,000 queries, and it should be very much accessible in less than 10 seconds, and there should be no lag. And this was ever growing. We expected growth like we have never seen before, and we eventually get that also. So if I had to ask a question, what is the logging platform that all of you use right now? No answers? Okay. Okay. Loki. All right. That are obviously the very great solutions. But as industry standard, Ashish mentioned yesterday, we also use ELK. So all our services that are running on EC2, ECS, EKS produce logs that are pulled by a FileBeat and pushed into Kafka. Then we have Logstash, pushed into Elasticsearch, and visualized on Kibana. This is the standard practice that everyone followed, and we have been doing it for a while. And it worked beautifully for us. But as the size of the logs increased, so does the cost. And we tried to reduce the cost by splitting the architecture of Elasticsearch into hot, warm, and cold tiers. And this reduced the cost for a bit and stabilized it for a while, but eventually, again, it kept on rising. So even after doing all the optimization we could, cost ballooned more than $1 million a year. There was operational complexity to manage a lot of Elasticsearch containers. And there was also requirement of additional paid features, like the audit logging that you cannot do, SSO if you want, you cannot do on that free version of Kibana. So we looked out for alternatives. These were pretty much available in the market. Splunk, New Relic, Grafana. So Trino, nobody wanted to use Trino as a logging platform, but we had Trino running. So we have multiple clusters of Trino running with hundreds of nodes and thousands of queries each day. And we have been doing it for a while now. And we were pretty confident that we are able to scale Trino to whatever extent we wanted. But ClickHouse was also getting traction in the market. Most of the open source community was also trying to use it. And They were not pretty there, but they were starting. And we did a small POC to get that. And we uh, got these results as a POC. So it has the continuous background merges. So if you know, if you're writing small files, then they are not very queryable by Trino. So Trino doesn't do very well with small files. You can vertically and horizontally scale, shared nothing architecture, full text search capabilities, and a very mature SQL syntax. I love that SQL syntax of ClickHouse. And it has extensive community support. You can reach out to anybody. They're ready to help. They are able to answer your questions. So this was a pretty great fit for us. We wanted to move ahead with it, and we did. So we didn't change the previous architecture. All the logs were still getting into Kafka, like they previously did. But we wrote a custom ingester. So it is a custom Golang SDK that's running. We did that and put all the logs into ClickHouse. That were multiple nodes of ClickHouse servers. Then we add a custom DSL in front of it. DSL, for those who don't know, is domain-specific language. We don't wanted users to query ClickHouse directly. We built a layer in between. And then it was made by again, custom UI, which was accessible to users. We will delve into each and every part of this and why we did this. I would like my colleague to take over.
Thanks, Anmol. As we said, like we decided to move ahead with ClickHouse, and ClickHouse in itself is a very amazing technology. It provides background merges. So the thing with Trino, the problem with Trino was we had a very nice experience with Trino, but if you ingest small files into Trino, it balloons to a very large extent, and the small files, when you read it directly from S3, that creates a searching problem. Trino, with its background merges, it can combine those small files into one large file and add compression to it. With the compression, we can reduce the size of the data that needs to be queried. And since there's less data to be queried, the queries automatically become faster. So that was the main turning point, like why we chose ClickHouse instead of Trino. Other open source projects, like they were too costly to begin with. At our scale, like you just saw that it was 60 terabytes, so the costs are mentioned per GB. Uh, with once we had that figured out that okay, we want to have ClickHouse in the picture, we started with that, and ClickHouse provides a very nice Kafka connector where it can listen directly from Kafka. So we already had our logs present in Kafka, and we did not want to touch this part of the code right now. So once the logs are already present in Kafka, we started first by using the ClickHouse Kafka connector and pulling logs from Kafka into ClickHouse. ClickHouse has a functional, by the way, ClickHouse also doesn't like too many inserts. So it wants us to batch the inserts at the client end. And they have added a functionality where you can insert the data asynchronously, and they would batch it at their end. We tried with that, but we just thought that it would put too much load on the ClickHouse server. And these are the things that we can pull out of the main underlying database and put it on a auto-scalable kind of architecture. So we built a custom Golang service, which will, ClickHouse also provides a Golang client. So the job of this client is to talk to ClickHouse servers, and it talks to them in the ClickHouse native format. So it does not cost any I/O at the ClickHouse end to transfer data between the service and the server. So we use that same client and segregated out the ingestion. Now we can run this ingestion nodes on spot instances and scale this based on the CPU utilization. These are resource-hungry jobs. Based on the CPU, we can scale them as per our as the load increases. So that helps. For the querying part, we built a custom DSL on top of ClickHouse. Now ClickHouse has a very good SQL syntax, and we could have given the SQL directly to the users. The users could write SQL queries. But the problem with that is that all the optimizations that we figure out, we cannot enforce them on all the queries. So we wanted to have a layer in between where we provide the query optimizations. Also, This makes our architecture very modular. So in future, let's say ClickHouse is an amazing piece of technology, but let's say some other database like StarRox, Doris, anything else comes to solve this problem in a better way, we can completely phase out ClickHouse and there would be no change required from the user's end. So we built a query and we defined our own domain-specific languages. And whatever customizations that we wanted to do, whatever optimizations that we wanted to do during querying. So if I want to give an example, let's say ClickHouse, when you insert the data into ClickHouse, the reason it is so fast is because you define a primary key for that data. And the primary key is basically the way the data is sorted within the tables. And when you query through the primary key, the results are very fast. But you can't enforce this for the users. So we wanted to enforce this in the custom DSL. So we have a primary key built in a way where we know that most used filters will be available in the primary key itself, so that the amount of data to be scanned is very less. So that was why we chose this. This is again built in Golang. We run this on spot instances. This is completely stateless. It does not do anything. There's one more thing I forgot about the ingestion part. It also batches the requests. So it will create a batch of 20,000. 20,000 is just a number that we came up to based on the size of our payload. And it batches up to 20,000 requests and inserts them into ClickHouse in one go. This reduces the I/O load on ClickHouse, and subsequently it improves the CPU performance and lower cost at the ClickHouse end. Then there was sorting and Bloom filter. Like I said, ClickHouse stores data by sorting it. So whenever it merges the data, it also sorts the data. So if the data is pre-sorted based on some primary key, it's very easy to search. The problem with logs is that a lot of time the messages are unstructured. And what Elasticsearch solves beautifully is that it tokenizes the messages and it creates an index on that token. They call it, it's an inverted index basically. And it's a very large index. So because it is a very large index, the cost also rises for the index itself. So instead of using an inverted index, we landed on a Bloom filter index. So we tokenize the words and create a Bloom filter out of it. What is a Bloom filter? Bloom filter is a probabilistic data structure. Whenever you insert data into ClickHouse, we tokenize all the words, and for each token, we have a fixed size of an array, which will just be a bitmap, which will store that does this word exist or not? What is the probability that this word exists? Now, the good thing about it is it can completely cut off the data where we are sure that this word does not exist. So, but it can still give some false positives where we have to scan the data. But again, it further reduces the I/O load on the ClickHouse servers. So we use that to speed up the searches. Then about the schema, I'm not sure if this is visible right now, but this column, the others column, we built the schema in a way so that we create a map out of it. We wanted our users to log not just a big string, because that would be like searching needle in a haystack. We don't want that. We want to structure our queries. And logs by nature are semi-structured. We can't force the users to just do just define all the data types for all the columns. So what we created instead was that we created a map field, and whatever extra fields that the users put in, we can put them in the map field. And in our query DSL layer, we explode this map field at the top level so that the users are unaware that how this is being stored at the backend. For them, it's just that they added a field in their data, and it was just visible for them. Codecs and compression. So ClickHouse shines with various compression codecs that it provides. One of the good things is the low cardinality field. So for the fields for which we know where we will not get a very high cardinality data. We can compress that very well. So ClickHouse stores data in a columnar format. For each column, we know if all the rows are same, it will just store one value, and everything else is same. So with this, we could like get 100x compression for some columns. Still, for the text columns, we would get about 7 to 8x compression, which is good enough for us. We have built a Bloom filter over top of it, so that works really well. Now, to further save the cost, we used a data tiering strategy on ClickHouse. So we have a hot tier which is stored on the disk. These disks are attached to the ClickHouse instances itself. And then there's a cold tier, which is the S3 bucket. ClickHouse can directly query the S3 bucket, and the data is moved from the hot tier to cold tier after 24 hours. Again, this saves us cost. And we can retain, like, theoretically, we can retain data forever, but we have a policy where we clean up the data after 30 days. Again, this can be managed through ClickHouse as well.
That is also configurable. You can just
that is also configurable per service. Like, if there's some financial data, we can hold it on for much longer. Coming to the front-end application, we did not want users to, like, Kibana works very well, and we initially thought we'll use Kibana itself and just implement the APIs. But then we realized that Kibana provides too many functionalities, and we also wanted to move to a more structured logging. And also, there were some custom things, like we wanted users to quickly switch between environments. So we could add a field that, add a drop-down that you can switch between production, canary, pre-prod, whatever you want. Then we added a histogram similar to Kibana. Like, Kibana was our inspiration when building our UI, because it provides a very good view of the logs data. And so a lot of our elements, the UI elements, they mimic Kibana in functionality. So initially, you can see that we built quite similar to Kibana. So we added a default field at the top where users can query the message field. And we thought that we could not get the users to actually move to structured logging. So we added a message field, but then that gave a wrong message that users are still searching on all the columns in the table. So we changed that structure to a more filter-like expression, which you can see in AWS console, or Grafana has a builder mode. So this is similar to that.
So when you are looking for, searching for data in Kibana, you are searching a document. We wanted users to get away from that perspective and think like, okay, you are not searching anymore, you are filtering. So you have to specify a specific column and then a value, then you will be able to do that. So once you move to structured logging, this becomes so much easier.
So, like, I've talked about structured logging already. Essentially, it says that whatever columns that you have to give them a structure. So this is the field, the message field. This would be a constant. This is like the type of log that we are generating. And whatever attributes that you have to put them in an attributes field. This is kind of like the structure defined by Hotel. So attributes like job ID, job ID and user ID. These kind of things go inside the attributes column. And then there's the resources, like what container is it running on, what host is it running on. Those things go inside the resource column. And this structuring saves us a lot of cost when we are actually querying for the data. Because we know, okay, we don't need to filter on all the data, just this column is enough. So next, we will talk about how to monitor these things. So for ClickHouse, like, we basically rely on the host metrics. ClickHouse has, we realize that our ClickHouse servers are mostly bound by CPU and I/O. So there's the CPU, disk utilization is not that great. Like, initially we faced some issues with disk utilization, so we started tracking it. But over time we realized that only the disk throughput is the limiting factor, not the disk IOPS or the disk total usage. So, and then there was network. We had enough network, so it was never a problem for us.
So you can always choose network type nodes in AWS if you are throttling a network.
Read-write bytes. This was one of the things that we could not figure out initially, that it was limiting on the read-write bytes, so we had to increase the throughput of the nodes, and this helped us a lot. Then on the service side, we track what are the number of new inserts that happen on ClickHouse. Each insert creates a new part in ClickHouse terminology, and this is the graph, which is quite similar to how our order tracking graph looks like. So as the rate increases, so does the logs, and so do the number of parts created. And we also track, like, ClickHouse does not like if you add too many parts, like too many inserts, and that is one of the primary problems with ClickHouse. Like if you insert too soon and it's not able to merge the parts quickly, it increases the number of parts and it starts rejecting all the new inserts. So we track that, and if it starts to rise, we basically take some action. And then we also track the resource usage, the query patterns, and like how the users are actually filtering the data, what is the time, like the telemetry data for our service, which is like how quickly can we return the result for them. And this creates a feedback loop where we know that, okay, this is the field that users are filtering on, and this is taking too long. Like we can optimize for the end of the spectrum as well, the tail end, and further improve our systems in the process.
So it's like a self-heal system. Users can obviously query on whatever they want to, and then there's a job that's running that analyzes what are the queries that are making and automatically suggests indexes on top of them with the configurations that they want. And okay, so they queried what they wanted, now we know what to put indexes on, and it's a loop.
Yeah, we also track the consumer lag for Kafka, because that is like the ultimate golden metric, because if that is getting affected, we know that we have to scale ingestion.
Yeah.
The ingester scales horizontally based on the CPU, so that is a good part. With this, we were able to achieve ingestion lag of less than 5 seconds. So we batch requests for 2 seconds, and we have kind of a buffer lag. We had a limit of 5 seconds, so we batch it for 2 seconds and just try to insert. And with this, we were able to do that. The P99 query time is 10 seconds. Of course, we cannot give results for all the queries in 10 seconds, but the tail end we can always optimize for. We have added stats and monitoring, so we can add alerts over it. The data is present in ClickHouse. We can do some pre-processing to generate metrics out of it and add an alert if we want. We have auditing capabilities. We know who searched for what, when, and how much time did it take. And the best of all, like, we saved $1 million in the process.
More than $1 million, actually.
So that was what's next. So of course, like, once we are done with the logging process, we want to move further into the other aspects of telemetry. So we want to add distributed tracing in the setup, metrics and alerting. Right now it's quite rudimentary, where we are searching on logs. It's not very scalable. Like if you want to add an alert on that, it creates too many queries to actually be helpful for ad hoc scenarios. Like this system is built for ad hoc scenarios, and generating too many metrics would actually slow it down. So we have to work on that. Of course,
for example, just a second, let me add to that. So we already have a metrics pipeline separately running. So we don't combine metrics, events, and logs. These are all separate things. But the problem with that is metrics that you have already defined are the ones that you know of. But if you want to do ad hoc analysis, and so something is broken right now and I want to fix it, or maybe put an alert so that it's not happening in 1 hour next, I don't want to do a deploy right now. So if you can extract metrics out of logs also, this is the problem. But apart from that, all the metrics pipelines are also in there.
So like this problem compounds when you have too many open source systems running. You can't put telemetry in a third-party system. So the best thing that you get is logs out of it, and you can add alerts on the logs. So this system should ideally cater to that as well, where you generate alerts out of logs and use that. Then we want to be fully OTel compliant, so that our system integrates very well with other systems, other new systems that are built in the observability space. Then there are some optimizations, like we could further compress the logs. There's a good compressor CLP processor which compresses the log really well, like the Spark logs could be compressed 200 times, like from some of the benchmarks.
So the magic of CLP is you don't even have to decompress the logs before, decompress anything before searching. So you can compress it and you can search while it is compressed. So technically everything works like you compress it and then decompress and then search. So CLP works like you can even do searching on compressed logs itself.
And then we want to provide better hints to the users. So we already have in the UI, like we provide hints that these are the logs that are coming, that do you want to search this? But we want to improve on it, build some model so that it's easier for the users to know, okay, this is the kind of thing that I need to search for. So we are working on it. Questions?
We explicitly booked time for this, okay, so it's your time. Yeah?
Yeah.
Okay. So you mentioned that you built a couple of modifications on top of ClickHouse and the front end in particular. Are you planning on open sourcing any of that?
Yes, we want to.
For a friend?
Yes, we obviously want to. But right now it's like too coupled into the system that we would eventually need time to decouple it and make it open source. And yes, we would definitely want that.
Very cool. Can you show a few dashboards wherein you have actually used these systems, and can you demo like what you have built?
So the problem with that is it would be running on production data and we don't have the legal clearance to show that.
Okay, okay.
Like we did not build a demo, sorry for that.
So it's typically exactly like this is. So this is a screenshot of demo data. So this is exactly what, so you can obviously have you can filter, so it's a plus minus button that you have, you can filter on any of the columns that you want to, histograms, you can do search on it, filters, you can switch between environments.
So I was more interested into seeing the grok patterns, and have you used, like, made any dashboards of actual user journey and tried to track it through?
We did not put, yeah, so user journey, like how do they, so that's in the pipeline, like we definitely track it, track the chunks of it, but yeah, obviously we can track like how the user, like what are the kinds of queries that he adds to the system so that we can improve our suggestion pipeline, whether
Sure.
we know that.
Thank you, thank you.
Have tables based per service.
Yeah.
So why that choice, and like how do you, if I'm trying to track something that goes from like the front end service to card service to payment service to this, like what is the workflow that you follow?
That is where distributed tracing comes into picture.
But for logs, is there no way for me to like track it
No,
through
for logs it's not there. So you can filter on order IDs and switch. You have to switch.
And you have to manually switch your service that you're going
Yes.
to. Okay, perfect.
So
And
if you
Like ClickHouse has a functionality to query across tables directly, but we typically don't want users to use that. So we want them to, when they are looking for traces, like look for traces, don't just combine everything into one. So
makes sense. And the second question that I had was like more ClickHouse specific, like when you're using sharded, assuming you're using a distributed table in ClickHouse, right? Behind the scenes, like what kind of machines are you using behind the scenes, and how sharded is your data right now for the kind of scale that you're using?
About 10 nodes.
It's M6G.16x last I remember. We started with C-type nodes because it's compute intensive. Then we added inverted index on top of that. Then our memory requirements shoot up. Then we shifted to M. That last time I remember it's M7G. I think M7G.16x large.
So Graviton with
and about 10 nodes you said, right?
So mostly it's CPU and IO bound. So as long as we are good with that, unless you use the inverted indexes provided by ClickHouse, the memory requirement is not that much.
Perfect. Thanks so much, guys. Really nice talk.
Sure. Thank you.
Any questions? Thank you. Great talk, Anmol and Palash.